Hello classmates, especially to our dear subject teacher in physics, Ma'am Helen Banwa. You are now watching the video presentation of Group 3 together with Group 6. I am Samara Dima, one of the reporter for today. We are now on Lesson 2, Mirrors. At the end of this lesson, you will be able to determine graphically, mathematically, the type of virtual and real magnification, location, and orientation of image of a point, and extended object produced by a plane mirror or a spherical mirror. As the past reporter had discussed, the image in a plane mirror has the same size as the object is upright, and it's the same distance behind the mirror as the object is in front of the mirror. A curved mirror, on the other hand, can form images that may be look larger or smaller than the object and may form either in front of the mirror or behind it. In general, curved surfaces can form any images, although some images may be so distorted as to be unrecognizable because curved images can create such a rich variety of images as they are used in many optical devices that find many uses, such as the camera lenses, magnifying glass, and telescopes, also in lighting system and laser applications. Curved mirrors. We can define two general types of spherical mirrors. A spherical mirror is formed by cutting out of a piece of a sphere and silvering it. It's either on the inside or on the outside of a surface. If the reflecting surface is on the outside of the sphere, the mirror is called a convex mirror. Then if the inside surface is the reflecting surface, it is called the concave mirror. A concave mirror has a silvering on the interior surface, just think of a cave, and a convex mirror has a silvering on the exterior surface. For a more understanding, let's start with a concave mirror. Concave mirror. We know that a piece of a cutout of a sphere is called a spherical mirror, right? So if the reflective surface is on the curve inwards, it is a concave mirror. Concave mirrors are commonly used in a shaving mirrors or a dentist mirrors, and it's even on telescopes. The reflective image is magnified, but the field of view is limited. Concave mirrors is also called as the converging mirrors. Convex mirror, on the other hand, similarly, the reflective surface is on the curve outwards, it is called the convex mirror. Convex mirrors are used extensively in car mirrors. Depending on the focal length, the reflected image is reduced its size, but the field of view is more. This is very useful to drivers, as the blind spots is drastically reduced. Concave mirrors are called fish eye or a diverging mirrors. You can recognize this mirror easily, as the outward bulge is quite evident most of the time. Let's talk about mirrors that aren't really straight. Last night, at the dinner table, my little brother was playing the spoon at his hands. I noticed that he is really staring at the spoon, and I asked him why. He then responded that he is wondering why whenever he looking at himself on the outward part of the spoon, he looked very funny, while taking it away and away he looked differently. Suddenly, he flipped the spoon, and now he is on the inward part of the spoon. He take it farther from himself, and whenever he brings the spoon closer to him, he get a magnified version of himself. He then asks me, what is happening? To discuss this, let's begin to talk about a special class of mirror, and it is called spherical mirror, a mirror that aren't really plain, right? To begin this, let's take a look at a huge spherical mirror and then we polish it very well, so it will be smooth. Now, let's cut out a thin size of this spherical mirror. To begin this, let's take a look at a huge spherical mirror. For example, this is a huge spherical mirror and then we polish it very well so it will be smooth. Now, let's cut a thin size of this spherical mirror. Imagine a line passing through the center of the sphere, which touches the reflecting surface at its center. This line is called the principal axis. The point where the principal axis meets the reflective surface has been marked by a point A in the figure. Point A is the vertex, which is the center of the mirror. The center of the sphere, from which of the spherical mirror has been cut, is marked by a point C in the figure. This is the center of curvature. The distance from the vertex to the center of curvature is your radius of curvature, denoted by the capital letter R in the figure. The point which lies midway between the vertex and the center of curvature is the focal point, marked by a capital letter F in the figure. The length measured by F in the figure is called the focal length of the mirror. It is the distance between the vertex and the focal point in the mirror. They are the distance. Although the figure is that it is a concave mirror, which is facing inwards, but the properties remain the same as well as on the convex mirror. The difference between them is based on the way they reflect light rays. There are also non-spherical mirrors like parabolic reflections. Consider rays that are parallel to the optical axis of a parabolic mirror. Following the law of reflection, these rays are reflected so that they converge at a point, called the focal point. A spherical mirror that is large compared with its radius of curvature. For this mirror, the reflected rays do not cross at the same point, so the mirror does not have a well-defined focal point, and this is called spherical aberration, and results in a blurred image of an extended object. Shows a spherical mirror that is small compared to its radius of curvature. This mirror is a good approximation of a parabolic mirror. So rays that arrive parallel to the optical axis are reflected to a well-defined focal point. The distance along the optical axis from the mirror to the focal point is called the focal length of the mirror. So a convex mirror or a convex spherical mirror also has a focal point. Incident rays parallel to the optical axis are reflected from the mirror and seem to originate from point F at focal length behind the mirror. Thus, the focal point is virtual because no real rays actually pass through it. They only appear to originate from it. For example, when you look in the mirror, it looks like you're standing on the other side of the mirror, but you really aren't. You are seeing a virtual image because the light rays that make up your reflection aren't actually converging to form an image view. Now, let's find out what really happens on the light rays on convex lens or on the convex mirror and what really happens in the converged lens or the concave mirror. On the convex lens, it bent outward, right? So as light rays enter the lens, they turn slightly towards the axis of the lens, the imaginary line that runs through its center perpendicular to its face. As they leave the lens and move back through the air, the rays are angled slightly more toward that central axis due to the lens curvature. The rays on the very top and the bottom of the lens are bent at a larger angle towards the central axis than the rays near the center, which stays almost parallel, and they all eventually converge at a single point called the focal point. What I can give you a great example for this is on a convex lens is the magnifying glass. So when we are using the magnifying glass on a sunny day, we can notice that the magnifying glass that we are holding and as the light rays come to the magnifying glass, we can see that the light rays only focuses on a single point where we can really notice it. As that single point, if we can point it to a object or for example in a paper, we can really see the light rays under the magnifying glass as if we point it on a object. It can create a small fire as the light rays only focuses on one point. Let's move on to the converged lens or the concave mirror. And when you look through the converging lens, you can see real images from objects that are beyond the focal point. This is because light rays from those objects actually converge after passing through the lens. And remember, when rays converge at a point, that means a real image has been formed. Let's take a candle that's some distance from the lens, which we will call the object distance. We will use the object distance and the focal length to find the image distance, the location where the image forms on the other side of the lens. Lenses have the same focal length on both sides, so we'll label the focal point on the side opposite of the object as f and the point on the same side as the object as f prime. Now we have that the ray traveling parallel to the axis will pass through the focal point on the other side. Let's draw a ray from the top of the candle, reflecting through the lens, and then passing straight through the focal point F. Since the focal length is the same on the both sides, we draw a second ray from the top of the candle through the F prime focal point, which then refracts through the lens and travels parallel to its axis. The third ray travels straight through the center of the lens. We draw this line because if we can consume a thin lens, then we can draw a straight line through the center and disregard the slight offset that would occur due to the refraction. With these three rays in place, we see that they intersect at a single point, representing the top of the candle in the newly formed image. And this both explains the convex lens or the convex mirror and the converged lens or the concave mirror. This explains why the spoon that my little brother was holding is representing a different reflection, where on the converged lens we can see that it is inward right and it is flipped upside down, which is that upside down reflection is what you really see there is the real reflection, as in the converged lens or the concave mirror has really a converged point. While on the convex lens or the convex mirror or the bent side of the spoon, we can see our reflection very well as it really imitates us. But in real life, that is just a virtual image of us, as the light rays imitates what it's really seeing. Let's proceed on checking your understanding or our understanding. And this is number 1. What happens when a ray parallel to the principal axis passes through a convex lens? Explain the illustration below in brief and concise. So as we remember, the convex lens is the lens that's facing outward. And in letter A, in the parabolic mirror, parallel rays from a parabolic mirror cross at a single point called the focal point. Because when the parallel light rays enter this lens, they converge at a focal point, making the image of the source. In letter B, in a large spherical mirror, what happens here is the parallel rays reflected from a large spherical mirror do not cross at a common point. It is because they are initially going in different directions, if we can notice. Then the image of the source generated by each individual ray are separate and do not cross at a point. And then in letter C, in a small spherical mirror, we can notice that parallel rays essentially cross at a common point, which is we can literally see the capital letter F represents the focal point and the small letter f represents the focal length. And then they are form a common point because the rays gradually diverge from each other. Check your understanding number 2. How does the focal length of a mirror below relates to the mirror's radius of curvature? Now, it shows a single ray that is reflected by a spherical concave mirror, which is concave mirror is
on the inward, then the incident rays is parallel to the optic's axis. The point at which the reflected rays crosses the optical axis is the focal point. The focal length relates to the radius of curvature of the mirror.
Good day everyone, classmates and especially Ma'am Helen. My name is Mary Jane Grande and for my part in this report, I will be explaining to you the topic of using ray tracing to locate images. So I hope that you will find this video informative and engaging. So when we look into a mirror, we see a reflection of ourselves. So have you ever wondered how the mirror creates images from the object in front of it? So the process involves a technique called the ray tracing, which helps us understand how light behaves when it interacts with the mirror. So ray tracing is like a drawing lines called rays and using the law of reflection to determine how these rays are reflected. So if you guys remembered, the law of reflection means or states that the angle at which light hits a surface is equal to the angle at which it bounces off that surface. While rays, on the other hand, known as light rays, are the paths that light follows as it travels from a source to an object or from an object to our eyes. For instance, if a light ray hits a mirror, it undergoes reflection bouncing off the mirror surface at an angle equal to the angle at which it strikes. So this reflection of light allows us to see our reflection when looking into a mirror. So similarly, if a light ray passes through a transparent object like windows or any object that is transparent, it undergoes refraction, causing the light rays to change direction as it enters and exits the glass. So simply, ray tracing allows us to find important information about the mirror, such as the focal point and image location. So this technique is also used for lenses, but instead of reflection, we use the law of refraction to determine how the rays are bent. So you guys, to locate the image of an object using ray tracing, we need to find at least 2 points at the image. So this requires drawing at least 2 rays from a point on the object and determining where the reflected rays intersect. So this intersection point is where the corresponding point of the image is located. So either it is in real space or in the virtual space. So to make ray tracing easier, we focus, of course, on the 4 principal rays whose reflections are easy to construct. So let's imagine we have a concave mirror, as you can see here in the example. You can easily identify the concave mirror because it curves inward or paloob, and the convex mirror curves outward naman or palabas. So with a corresponding arrow-shaped object in front of them. So yung nakalagay dyan na pangalan ng object, may nakalagay dyan na name ng object, yun yung magre-represent as the object in front of the mirror. Okay? So we have an example here that were stated in the module provided by Ma'am Helen. So it starts by drawing rays from a point on the object that is mapped on the optical axis. So as I can see here, it chooses to draw ray from the tip of the object. So principal ray 1 travels from a point called Q or the letter Q and moves parallel to the optical axis. The reflection of this ray must pass through the focal point in the case of a concave mirror. So the reflection of the principal ray 1 goes through the focal point of letter F. And in the convex mirror, the backward extension of the reflection of the principal ray 1 goes through a virtual focus or a point behind the mirror. Next is the principal ray 2 travels on first on line going through the focal point and is then reflected back parallel to the optical axis. And the principal ray 3 travels towards the center of the curvature of the mirror and strikes the mirror at the right angle or in the normal incidence. It is then reflected back along on the same line. Finally, on the principal ray 4, it strikes the vertex or the center point of the mirror and is reflected symmetrically about the optical axis. So by following these ray tracing rules, we can determine the location of the image formed by the mirror. So now let's relate this to a real life example. So imagine that you are standing in front of a mirror, like the ones you have in your room or in your bathroom. So as you face the mirror, you see a reflection, of course. The point where all the reflected rays from different parts of your face converge is the location of your image. So this is the point that you see in the mirror. While the focal point on a concave mirror is located in front of the mirror closer to you. When the mirror reflects the light rays from your face, it manipulates them in such a way that they converge at the image location behind the mirror surface. This is how the mirror creates a virtual image of your face. So guys, understanding the concept of ray tracing and how light behaves in spherical mirrors is important in various fields such as the optics, photography, and even computer graphics. It helps us explain how images are formed and located. So the next time you look into a mirror, remember that the image you see is the result of the light rays interacting with the mirror surface and following the rules of reflection.
So next is the ray tracing rules. So we have here summarized references. So ray tracing is important to it's very useful for mirrors because it can accurately show how light reflects off a mirror surface, making the reflection look real. It's like virtual mirror that acts just like real one, showing what's in front of it. So the first summarized rule of ray tracing rules is a ray traveling parallel to the optical axis of the spherical mirror is reflected along a line that goes through a focal point of the mirror. Imagine if you have a curved mirror like yung sa kutsara or let's say spoon. So the optical axis is just imaginary line through the center of the mirror. If you shine a laser beam parallel to this line, it will bounce off the mirror and go through a special point called the focal point. It's like the mirror is making the light meet at the point. So when a light ray moves in a single line parallel to the center of the mirror, it bounces off and goes through the focal point, just like the way light reflects off the inside of the spoon. The next one is a ray traveling along a line that goes through the focal point of a spherical mirror is reflected along a line parallel to the optical axis of the mirror. Next one, we have a ray traveling along a line that goes through the center of curvature of a spherical mirror is reflected back along the same line. Imagine you have a shiny ball cut in half. So the center of curvature is just the middle point of this ball. Now, if you shine a laser beam towards the mirror, passing through the center of curvature, the light will bounce off the mirror surface, go back along the same line. It's like the mirror is sending the light back exactly the way it came, just like the way light reflects off a shiny ball. So the last one, a ray that strikes the vertex of a spherical mirror is reflected symmetrically about the optical axis of the mirror. When a ray hits the center of the round mirror, the angle it hits is the same as the angle it reflects away. But on the opposite side of the invisible line, it's like a ball bouncing back symmetrically if it hits the center point of the perfectly round mirror. So what is mirror equation? It is an equation relating object distance and image distance with focal length is known as a mirror equation. It is also as a mirror formula. So, mirror equation is used to calculate various aspects of an image formed by a mirror, such as its position, size, and nature. It helps us understand how light rays reflects off a mirror and predict where an image will appear when object is placed in front of the mirror. In a spherical mirror, the distance between the object and the pole of the mirror is called the object distance. The distance between the image and the pole of the mirror is called image distance. The distance between the principal for focus and pole of the mirror is called focal length. In ray optics, the object distance, image distance, and focal length are related as 1 over v plus 1 over u is equals to 1 over f. Here's what each terms stands for. So u is the object distance, or where the object is placed. For v, the image distance, or where the image appears. And for f is the focal length of the mirror given or by equal to r over 2, and r is the radius of curvature of the spherical mirror. R, distance between the mirror surface and its center. Center of curvature is the midpoint of the mirror sphere.